Hey there, folks. Good morning. Let's do a problem that involves a concept known as rolling without slipping. Here's our problem description, which you can pause the video to take a look at if needed. However, I'm going to just jump directly into the picture. We're given a uniform hollow disc that hangs from two supporting wires along its outer edge. I'll refer to its inner radius as R1 and the outer radius as R2. Let's also add a set of coordinate axes off to the side. I'm going to set the upwards direction as positive and the downwards as negative. If you would rather set it the other way around, that's totally fine too. Your choice. Initially, this disk isn't moving, but after a small period of time, one of the supporting wires will break, causing the disk to fall 2.20 meters. During that fall, the disk will roll without slipping along the other wire, and it's our job to figure out the speed of the center of the disk after it falls. Let's use that 2.20 meters value as the initial height of the center of the disk, and then once it falls, the final height will be 0. The problem description told us to solve this using energy conservation, so let's grab the equation for that and get started. The first thing we can do here is eliminate the other work term. We can do that because there's no friction or dissipative forces going on here, so the value of W other is just 0, and we can get rid of it. Next, let's make a modification to the kinetic energy terms. We have translational and rotational kinetic energies here, so we need to have terms on both sides to account for that. I'll use a capital T subscript for the translational and a capital R for the rotational. On the initial side, which is before the disk starts rolling and falling, there's no movement whatsoever. Remember, it's just hanging there stationary. Thus, we can set these initial kinetic energy terms to 0 as well. There's one more elimination that we can do over on the final side. In our picture, I set the final Y value to 0, which means the final potential energy is going to be 0 as well. Let's clean up these 0 terms before moving on. The next step is to plug in some definitions. For the left-hand side, we have mg y initial. Then on the other, we have the translational kinetic energy of 1/2 mv squared, but I've replaced v with v center of mass, which will represent the velocity of the center of the hollow disk. And finally, we also have 1/2 I omega squared for the rotational kinetic energy. Before we move on, let's review a couple things. Whenever you're told that something rolls without slipping, it means that the velocity of the center of mass of that object is equal to r omega, where r is the object radius and omega is the angular velocity. In this situation, the hollow disk is rolling along its outer radius, r2. So we need to exchange r for r2 in this equation. Also, the moment of inertia expression for a regular disk won't work here. We don't have a single radius. Instead, we have 2. So a more appropriate expression would be the moment of inertia of a hollow cylinder. So let's combine 2 steps here. The first one is to take our rolling without slipping equation, divide both sides by R2, and then plug that ratio into our rotational kinetic energy term for omega. And the second step will be to plug in that entire moment of inertia expression for a hollow cylinder in for I. And here's what that looks like. Notice that we end up with mass on both sides. Let's cancel that out and move on. Next, I'm going to distribute this first 1/2 coefficient into these parentheses. And then we can drop the outer parentheses since they're no longer needed. Let's distribute again by sticking this 1/4 coefficient into the next set of parentheses, like this. And then after that, we should square the numerator and denominator of this ratio in our last set of parentheses, and then distribute the result into these parentheses, like this. We get an expression which has an R2 squared in the numerator and denominator of the final term. I'll cancel that out and then factor the V center of mass squared quantity from each term on the right. And that allows us to combine this 1/2 and 1/4 inside the parentheses together and turn it into 3/4. Nice. Let's divide both sides by the sum inside the parentheses here, and then we'll take the square root of both sides. Here I've included a plus or minus sign on this square root because earlier we set the downward direction as negative. And since the disk and its center move downward during the fall, the center of mass velocity needs to be negative as well. It doesn't make sense physically if we have a positive square root result here. So we can use the negative root to stay consistent with our choice. And there we go. If we insert all of our numbers, here's what that looks like. And when that's entered into the calculator, we get a final answer of approximately negative 5.07 meters per second for the center of mass velocity of the hollow disk. And again, the answer is negative here because of our coordinate system choice. If you set the downward direction as plus y, well, then your answer would be positive 5.07. So it all just depends on what you chose in your picture. That's it for today, guys. Thanks for watching.